Resonance in the Vocal Tract by Daniel King, a project for Physics 374 taught by Dr. Amy Colin at St. Olaf College in Northfield, Minnesota. What happens when we sing? Fundamentally, the mechanism of the voice is a Bernoulli-based process in which the vocal folds convert a DC current of your breath into an AC set of harmonics. However, before the world hears your lovely voice, it needs to travel up to the opening of the mouth, which is a distance of about 15 to 20 centimeters named the vocal tract, which will greatly affect the quality of the sound that comes out. So, we could say that the output spectra we hear in a recording is a product of some source spectra generated by our vocal folds and a filter resonance spectra, which is determined by the size and shape of our vocal tract. We have a pretty good idea of what the source spectra looks like. Like all wind instruments, the vocal folds produce a fundamental frequency in its harmonics. But how could we determine the resonance spectra? Well, one could imagine holding the source spectra constant in all frequencies, such that peaks in the output spectra are going to be determined solely from peaks in the resonance spectra. It turns out that we can do this pretty well in the voice through an aperiodic technique known as vocal fry. Because this aperiodic technique should produce frequencies across the board, if we record the sound, the only frequencies that should stick out will be those resonating with the vocal tract. Alright, so here's the power spectra of vocal fry. On the bottom axis we have time, and on the left axis we have frequency, and the redder the color, the more intense that frequency is at that moment. And here's what it sounds like. Alright, so it's not the most beautiful sound in the world, I'll give you that. But look, even though we're using this aperiodic technique that should have, frequencies all over the place, we still get these discrete bands of resonance in our sound. But where do these come from? And furthermore, these definitely aren't the harmonics of a note being sung, but they do seem harmonically related. For example, if this could be considered a fundamental, then this lines up well with 1F, 3F, 5F, 7F. So we have the odd harmonics of a note? What's going on? The following argument for why this is follows a paper by Wolfe et al., which was published in 2009. Our model for the vocal tract is as follows. Sound is created at the glottis, represented by a small constrained region of the tube, and travels through the tube, representing the vocal tract, to the mouth, represented by a large open end of a tube. We have a two-step approach to solving for the resonances of this model. First, figure out the resonances of a simpler model that consists of a tube with two open ends. Then, we can analyze how these resonances change as we constrict one side of the tube to be small, like the glottis. When sound is produced at the glottis in the double open tube, it will travel down the tube and will be reflected at the other end with a phase change of pi. Depending on how this wave interacts with itself after reflected, it will make it either easier or harder to produce sound at the glottis. For example, a frequency with a wavelength that is 4 times the length of the tube might travel along the tube like this. When the wave reaches the open end of the tube, it will reflect with a phase change of pi, and the pressure wave will retrace itself as it reflects from the front of the tube. The other wavelengths at which this occurs are easy to find. They just need to have a maximum where the sound is produced, and a zero at the right end of the tube. These constructive interferences produce a large pressure antinode where the sound is produced at the left end of the tube. Destructive interference, on the other hand, occurs halfway in between these constructive wavelengths. At these wavelengths, when the phase change occurs, the wave traces the opposite of itself as it travels back to the glottis, which combines with the incident wave to create a pressure node at the left end of the tube, where the sound is produced. So, which one of these interferences is better for singing? Well, it turns out that resonance occurs in the vocal tract when there is a maximum of flow at the glottis. But what is flow? Well, we can think of sound as the propagation of some periodic displacement of air molecules. So, we could write that y, the displacement of air molecules at the glottis, is proportional to some periodic function, such as cosine omega t. Flow, then, is going to be proportional to the velocity of this displacement, or dy dt, in this case proportional to a sine function. Pressure, on the other hand, is related to force, and is thus proportional to the acceleration of this displacement, or the second derivative of y, making in this case proportional to a cosine function. All of this is to say that, because of the dependence of these different components of the sound wave, pressure and flow are out of phase with one another. Thus, pressure nodes correspond to flow antinodes, and pressure antinodes correspond to flow nodes. So, to attain maximal flow as is desired, we want to aim to have a minimum amount of pressure at the glottis, or a pressure node, and thus a flow antinode. Thus, it is wavelengths of destructive interference and pressure that correspond to resonant frequencies in the double open tube. Now let's see how this changes as we constrict the left side of the tube to more accurately model the glottis. The result is that the wavelengths at which there is maximal flow will change drastically, as now in order to produce a large amount of flow at the glottis, the wave needs to accelerate the gas in what is now a very constrained region. From writing that pressure equals force over area, we see that when you decrease the size of the area, the same acceleration of the gas around the glottis now requires much more pressure, kind of like blowing through a tiny straw. In contrast, the frequencies at which there is maximum pressure hardly change, as these frequencies have flow nodes at the glottis and are thus unaffected. To restate, as we constrict the opening of the tube, the frequencies of maximal flow now require more pressure, while the frequencies of maximum pressure hardly change. Thus, it makes sense that in the limit as the area of the opening of the glottis goes to zero, the resonant frequencies of our constrained tube become those of maximum pressure at the glottis, the constructive interferences. With the actual size of the glottis compared to the vocal tract, we should expect the resonant frequencies to be very close to and just above the frequencies of constructive interference. This explains the harmonic relationship observed between the different resonances. The frequencies of maximum pressure at the glottis occur in a series that gives a fundamental resonance, 3 times that fundamental resonance, 5 times that fundamental resonance, and so on. But how good is the model at predicting the fundamental resonance? Well, the average length of a vocal tract is about 15 to 20 centimeters. I have a decently long neck, but I think my Adam's apple, where my glottis is pretty high, so a good estimate might be about 18 centimeters. Calculating the fundamental resonance predicted by the model from the speed of sound and my estimation gives us a fundamental resonance of about 476 Hz. The actual value is about 398 Hz. Not bad at all, considering that I very well might have underestimated the length of my vocal tract. The model would predict I have a very large vocal tract of about 22 centimeters. However, the model is far from perfect. It compares much less well for different vowels than the one I sang in this video. To summarize, each frequency in the sound produced at the vocal folds propagates up the vocal tract with more or less efficiency depending on how it interacts with itself. This creates resonances in the vocal tract that can be observed using aperiodic techniques like vocal fry. A basic model of a tube with a constrained end was used to approximate the first 2 resonances in the vocal tract. The length of my vocal tract was estimated, and the frequencies predicted by the model were shown to be decently accurate for the vowel h as in heard, but is far from a comprehensive model. A huge thank you to the Voice Vista Power Spectra Analyzer, the University of New South Wales website, and Dr. Amy Colin for all being great resources in the making of this project.